Hello everyone, I'm Rodrigo Benenson, and this is a tutorial on human-in-the-loop annotations. This is part of our ECCV 2020 tutorial on weekly supervised learning for computer vision. Since this is a recording, please do follow through the video and write down your questions and bring them in the question answering sessions we'll have in the allocated slot for this ECCV tutorial, or write them down in the comment section if you're watching this video in a video hosting platform. We'll do a fair effort on trying to answer them. So typical machine learning papers focus on a small part of a full system. For instance, a paper might propose a new architecture and argue that the new architecture is better than the old architecture, or they might propose a new loss for training this architecture and argue that the new loss is better than the old loss, or they might actually modify the training loop, for instance, to have a better distributed training and argue that this new training strategy B is better than the old training strategy. So this system of architecture loss and training loops is what common papers cover. However, practitioners know that this full system is only a small part of what you need to implement and deploy for practical applications. And this diagram is just one of those diagrams that show what else is involved into building a real-world machine learning pipeline. So even if you abstract yourself from the full pipeline and you only look at the data part of the system, then there's still quite a few complexities on the data collection part. So the first step usually is to collect some images that are in your target domain. Then you will collect some annotations on top of those images. And then with those annotations, you will train a model using a subset of all the data available. And then using the remaining data, you're going to evaluate your model to decide if the quality you obtain is good enough or not. If it's not good enough, then something needs to be done. One typical thing that will be done will be that instead of using this naive pipeline shown here, you likely start from a pre-trained model that's been trained on some existing similar images and annotations that's been trained maybe in a similar manner as your target model, or maybe different if you have different type of annotations or you try to maximize generalization. And in practice, this transfer learning strategy is shockingly effective. So always do consider looking for data sets that are somewhat similar to your target domain. This will most likely help your final results. And there's some people in our community that argue that there's some kind of threshold on which if the model has seen enough of the real world, then most application domains will become future learning problems. However, if the pre-trained model is not enough, then the next most common practice will be to start collecting more annotations. This is much easier than trying to modify the architecture or the training procedure of your model, and it's most likely to provide better results because then you're providing system with information required to perform well in the application domain. Sometimes you also even need to collect additional images to further increase your training data availability. However, it turns out that collecting more annotations is a subtle matter. And if you think about it, I will make the argument that you want to involve a model when collecting the annotations. You shouldn't be annotating data in blindly. You should use the model to drive this annotation collection. And this is commonly called human-in-the-loop annotations because the human is providing the annotations that will complement the model, on which you will train a new model that will drive new annotations and then train a new model, and so on and so on. So human is part of this loop of training and collecting more data until you obtain a good enough quality as a final result. So let's discuss how this annotation process will go. So let's assume that you're trying to do a pixel labeling task and you are shown this cat image, and then you say, well, I'm going to scribble this area to indicate that it belongs to cat. That seems fair enough of an annotation. And then you train your model with this new annotation and you obtain this result and you see how the new mask is covering the area annotated. So it was a good annotation. However, the caveat in this reasoning is that it's not accounting for the fact that before training your model, this was the mask that you got. So just annotating blindly without inspecting the output of your model is likely to generate redundant annotations. You're spending time annotating areas that the model already knows how to handle. You don't want to do that. Another scenario is that you might be annotating, for instance, a mistake here on the back of the cat, and then you train your model, and the result is no large improvement. So some areas of the visual space might actually be too hard for the model to learn. This usually happens if you take very adversarial cases, or if you look at very rare cases that the model anyway is not going to capture because there's not enough signal for that part of the visual space. So in practice, you want to collect data that is both informative for the model and learnable for the model. So in this tutorial, we're going to talk about detection task, where you're asking yourself how to add additional boxes in my training data, and semantic labeling task, where you're wondering which pixels should be adding to my training data. So the first question you might wonder is which image area should be annotated then? And this is usually the area of active learning problems. And it can be formulated as which annotation is going to lead to an improved model? Which annotation is going to lead to the most improved model? And this is a very hard problem. And then what do we do in our community when we have a very hard problem? We use heuristics. So let's discuss some of the heuristics that have been used in this domain to try to increase the chances of obtaining useful annotations. So the very first baseline you should consider, and is commonly used, is to just do uniform sampling. You do accept that you are ignorant and that maybe using the model is not done in the right way, and you just do uniform sampling. And it's as simple as it gets. It's a reasonable strategy to bootstrap your annotations, but there are some caveats, of course. First one is that if your model is reasonably good, then you will have a high portion of redundant annotations. And this is a problem, as described before. You're wasting human time. And also, if your class distribution that appears on the image is very skewed, then the classes that appear the least will be underrepresented in the data you have collected. And that can be an issue when you train your model. So there are some variants. For instance, if you have image level labels, then you might want to do uniform annotation, but only across the classes that you know the model is underperforming. So this is something you should keep in mind. It should be in your system as a baseline, and it's trivial to implement. Another intuition or idea that comes up in some papers is this idea of which I'm calling score bands, where given the score output of your model, if you look at the argmax class, then you look at how strong is that confidence on the output that the model has, and then you can take some kind of range, either the pixels where the score are around 0.5, so the model wasn't very sure, or the scores which are not fully confident. So maybe it's a region where it's relatively high confident, but maybe making mistakes and you want to correct. So this is very simple to implement. You can easily target ambiguous regions by this notion of ambiguity. And because now you're using a model, you can more easily aim for class balance sampling. However, empirically, this is shown to be not a very effective strategy, albeit intuitive. So the simplest strategy that provides the better results is the high entropy measure, or the entropy measure. And this is the one baseline you want to have in your system. So here I'm representing the output of my softmax projected into a three-dimensional space, so I can color code an image. And then the areas that have an homogeneous color is areas where this bright homogeneous color is an area where there's high confidence on one single class. Let's say in this example, class 2, after the softmax has a high probability score, while the regions that are more moderate colors are the one where there's more confusion. And the entropy measure allows you to measure low confusion and high confusion region, and this is simple to understand. And then if you target high confusion regions, you're guaranteed to provide training loss in your model with those samples, because you're committing to one class, and then this would push the model in a different direction. And empirically, this is the baseline that is hard to beat. Most methods that are proposed improve only marginally on top of the entropy heuristic. One of the caveats that this approach has, and that many other methods actually do have too, is that, for instance, there's no notion of sample diversity. So it might be resampling very, very similar pixels or boxes across different images without being aware of it. And this is also not the most efficient samples you can collect. Another very common approach is that instead of training a single model, you're going to train multiple models and then compare their outputs on a given image. And then you can measure the disagreement using L2 norm or some divergence or some specific form of entropy. And because you have multiple models and you're comparing them, then you have a better estimation of such model uncertainty, which is what you want. You want to model in the areas that the model is likely to be wrong. And because you're using multiple models, this tends to provide better results than a single model. Of course, one of the caveats is that you do need to train multiple models, so that makes the process a bit slower. Some people try to work around this by mimicking an ensemble using a dropout strategy on a single model. That works to some extent, but less good than if you do have multiple models. And another caveat that I want to mention is that if you're going to train multiple models, then you can use the average output of this ensemble as if it was a single model, and then use the high entropy measure over that. And that in practice tends to be also quite competitive. The last idea I want to mention as an heuristic for annotation selection is a recent one that highlights the notion of self-consistency. One of the outputs you want to have, one of the characteristics you want to have of the output of your model is some notion of equivariance. So if you translate your image, you would like the score maps to be translated. And in this paper, they propose to do so by doing some kind of affine transformation in the doing some kind of affine transformation in the inputs, running these two different images through the model, and then because the transformation is known, you can compare the two outputs and check how similar they are. You either compare it directly, or you first compute the uncertainty per pixel and then you compare that. But this mismatch is what is going to inform which region should be annotated. And this does require double test time because you're running the model twice. However, since in this process you're going to retrain a model, that usually is a negligible cost, and it does require you to handcraft whatever is this test time data augmentation. However, most application domains this is relatively easy and well known. So this strategy actually should be used as a complement to the previous one, and thus provides also improved results. So this is a personal opinion, but inspecting papers and reading about them, I basically believe that the active learning field is full of very interesting ideas, but most of them work very little or only work sometimes. So they will show interesting results on MNIST, but this will hardly transfer into real world scenarios. So you should read this paper with a pinch of salt. And there's a bunch of interesting ideas that have been explored. I put some citations here of interesting work that you should check. For instance, there are methods who try to estimate how likely is a sample to change the model parameters. So use a Bayesian strategy to estimate this, and this on principle should be better, but this estimation is hard to do. Some other methods propose to actually learn the active learning strategy, either directly from data or through reinforcement learning methods. Or some papers actually propose to not only account for how the sample is going to improve the model, but also account for the time it will take for a person to annotate. So if you have two samples which are equally good for the model, then you want to pick the one that's going to be easier to annotate for a human. So do check these references if you're curious about it, but in practice, if you're in doubt, just use an ensemble model because that provides the better quality. Use an entropy measure to select the areas, and then if you want, you can also add the self-consistency to get a few more bonus points. So let's talk some particular examples of active learning strategies that have been done for bounding box annotations. So in this paper, they propose to annotate bounding boxes without ever drawing any bounding box. So they initialize their model using image level labels, and they use a weakly supervised technique to obtain an initial detection model that then will run over an image. And then after non-max suppression, they will basically pick some boxes to ask a human annotator to verify. And they will pick this based on some of the heuristics similar to the ones I mentioned before. And then the annotator will say either this box is correct or incorrect, or they might also provide some more detailed comments like is it missing the object or is it part of the object. However, all of these inputs are only keyboard inputs and no annotator is ever drawing any box. And with this strategy, as any paper, they show that this does provide improved results. So if you compare the resulting model quality compared to the human annotation time it takes, if you start only from image level label, you get some weakly supervised model here, and then as you collect more annotations, your model keeps improving. If you add boxes that are just drawn randomly, then this improves quite slowly, while if you're doing this simpler, quicker, yes, no answers, then you're collecting useful data for the model faster. And these are some qualitative examples of how the initial model weakly supervised from the image level labels looks with the red boxes, and after collecting the yes/no answers, how the model has locked in the extent of the objects, despite never any box have been drawn or being corrected. So this is an example where you can go faster by guiding the questions using some intelligent strategy for annotations. And there's some related work here that explore other active learning strategies for object detection bounding box collections. So let's look at an example where we're going to do active learning for guiding which area of the image is going to be segmented. So this work starts from an insight which was highlighted by a recent paper, where in most work for semantic segmentation, given an image, you're going to try to basically label every single pixel. However, in this paper, they highlight that actually this is not needed. Most convolutional architectures operate per pixel, so you might as well also just take arbitrary regions of your image and then annotate only the subparts. As long as during your training you mark, in this example, the black region to be ignore regions for the loss, then your convolutional model will train just fine, and also you can evaluate just fine with this kind of data. So this gives a freedom on annotating on a subpart of the image, and then the one wonder which area to select. So this previous work I mentioned about self-consistency through equivariance explores that idea. So they used this transformation in the input, they apply the model, they look at the difference, and then they select the region to annotate based on the uncertain regions that are most different across these two transformations. And then they pick an arbitrary 100 by 100 pixels regions that they're going to annotate. And then having annotated densely these regions, then they can retrain the model and keep looping around this. And of course, as any paper, they show that this is quite effective. So if you go into annotate some regions randomly, then this improves the quality of your model, but rather slowly. If you instead use a high entropy measure, then this is a green line, which is the strong baseline. As you can see that the proposed method is slightly better, but not a lot, which is the black region, the blue line that should be compared to the fully supervised black line. And you can see that as you increase the annotation budget, then you eventually converge to the fully supervised case, but the way it raises is quite fast. So here they claim that, for instance, with only 12% of the pixels annotated, you get 96% of the full supervised case. And the final two curves show what happens if you actually use this self-consistency aspect also during the training of the full model. This improves the fully supervised results, and of course then also improves the weakly supervised results. So the main takeaway here is that the segmentation blocks that you're going to annotate can be machine selected, and this will allow to get high quality with fewer human annotation time. Another example of collecting segmentation data is to explicitly guide where the annotator is going to annotate, but even more fine level. So here, instead of using active learning, we do allow the annotator to choose the region they're going to annotate, but this is heavily guided. So we start from images and bounding boxes, and we try to do per instance masks corrections. So we have an initial model that has been trained through transfer learning, where given an image and a box, it will generate an initial mask, and then we're going to ask the annotator to only do clicks. So they will click on a background region to indicate it should be foreground, or they will click on a foreground region to indicate it should be background. And we limit the number of clicks the annotator can do. And that way we limit the time they can spend on this task, but they're free to click on any part of these masks. And then we use a second model who has been trained with also transfer learning that can take the image, the mask, the box, and the clicks, and then provide an improved mask. Either that's good enough and we're done, or then the annotator is asked to do a few more clicks until the quality has converged. And this has been shown to be quite effective. You get high quality models that if you only do Coco polygons, while using about a third of the time for these instance mask annotation tasks. So here at the bottom, you see some examples of how the annotated masks look when things have gone well. And these are the results of the box plus the clicks. And we did annotate about 2.5 million instance masks over 300 categories this way. And this whole question of given an image, a box, and some clicks, how do you generate the better mask is a whole subdomain of research And one of the recent papers shown at the ECCV conference is the one cited here that does even better on exploiting the human annotations that go after the mask, after the bounding box. All right, so one last idea I want to share with you. It's an area that is somewhat underexplored, but I think it's a really sweet idea, so I would like to share with you so you know about it, which is this idea of annotation dialogs. So it turns out that if you think about it, probably the best strategy to best use the human annotator time is not to fix to have a single question type, but actually allow to have different question types and then let the machine choose. So you're not only letting the machine suggest where to annotate, you're also letting the machine suggest what to annotate, what kind of questions to answer. And a few sparse papers have explored this idea. In this example, for instance, the system estimates the effort it will take to provide the new annotation and the complementary information that such annotation will provide. And then the system will select which image and which type of annotation should be marked, should be answered. So in this example, it would be asking, provide me a label for this region, or provide a full segmentation and labeling for this other image. And here's another one of those papers where they show that there's different type of human tasks that can be done. And then there's a stateful system that will know about the existing annotations, the state of the partially trained model. And then based on that, they will figure out which question to ask on a given image that is the best trade-off between information gain and human time. So this is the area of annotation dialogue, where basically the machine and the human having a conversation around the dataset. And this is an interesting area that should be further explored, in my opinion. So that's about the time we had today. So let's discuss some takeaways. First off, if you're going to have a large annotation campaign, it seems to me that a hybrid annotation strategy, where you have some weakly supervised and some less weakly supervised or partial full supervised annotations, is the better use of human time. And as we scale up the annotation campaigns and processes, this is likely to become a more and more common practice. Similarly, if you're going to do strong annotations, please keep in mind that these don't need to be dense and full. They can be partial and focus on whatever the machine suggested to focus on. If you're going to have an active learning component, please do keep it simple and be aware that some of the fancier methods might be underperforming in practice. And let me restate how effective is transfer learning in practice. Do not underestimate the effect of just throwing more data, even if it's not directly related at the problem. And finally, you might have seen from this presentation that there is a large design space of human-machine collaboration when it comes to learning a model. And I think there's quite a lot more to be done in this area, and I invite you to explore it too. So I hope you enjoyed this talk. I invite you to watch the other videos of this tutorial. Some videos talk about weakly supervised object detection techniques. Some video talk about weakly supervised pixel labeling techniques. And some of the videos talk about the challenges we have when it comes to evaluating weakly supervised methods. I hope you have a good day. Bye.